Welcome, curious minds, to another deep dive into the information you need to feel truly well-informed. We know the sheer volume of climate change news can feel, well, overwhelming, like trying to drink from a fire hose.
Absolutely. It's a lot to keep track of.
But that's precisely what we're here for, to give you a shortcut, a clear path through the complex landscape, a cutting edge, and frankly, mind-bending strategies being discussed to tackle this global challenge. Today, we're not just going to scratch the surface. We're going to dive deep into these ideas, explore the science behind them, and try to understand their broader implications for all of us. Okay, let's unpack this.
Sounds good. It's important territory.
Our mission today is to venture beyond just emissions reductions, which of course remains absolutely critical. Can't stress that enough.
The foundation.
We're stepping into the realm of intentional, large-scale interventions in Earth's climate system. Imagine strategies so ambitious they aim to alter our planet in fundamental ways, either to cool it down directly or to remove the excess carbon we've already pumped into the atmosphere.
Yeah, it's a fascinating and sometimes, startling exploration of where science is potentially taking us and what the consequences might be down the line.
Exactly.
And what's fascinating here, I think, is how these two distinct families of technologies offer very different pathways to addressing climate change, even though they share the same ultimate goal, right?
Right. Different paths, same destination, maybe?
Sort of. On one side, we have carbon removal, or CDR. That's about tackling the root cause of the problem, the accumulation of CO2 in our atmosphere. Think of it as, actively cleaning up the carbon mess we've already made.
Okay, the cleanup crew.
Exactly. And then on the other side, we have solar geoengineering, or SG. This aims to manage a symptom, the rising global temperatures. So fundamentally different approaches, each with its own unique set of opportunities, but also crucially significant risks.
And for this deep dive, we've pulled from some truly incredible sources. We've got detailed field trials from the U.S. Corn Belt specifically on enhanced weathering that give us tangible, real-world results. Really interesting stuff there.
Oh yeah, that study is quite something.
Then we're looking at comprehensive reports exploring the global implications of geoengineering on everything from how it might affect sustainable development goals to its impact on complex economic models. Our mission is to break down these complex ideas, share some surprising facts, and reveal the so what's for you, ensuring you gain knowledge quickly and thoroughly without feeling, overwhelmed. So let's get started on this deep dive.
Let's do it.
So first things first. Why are we even talking about these large-scale climate interventions? Why do we need something beyond just cutting emissions, which seems like the obvious first step?
That's a crucial question, and it really sets the context for why these interventions are even on the table, why they're being seriously discussed. The stark reality is that despite global commitments, like those made in the Paris Agreement, current emissions reduction pledges are, unfortunately, likely to lead us to an average global warming of around 3 degrees C by the end of this century.
3 degrees Celsius, that's significant.
It is. This isn't just a number. It's a profound shift for our planet. And why does that 3 degrees C matter so much to you, to all of us?
Yeah, tell us.
Because climate change is already having detrimental effects on our collective goals for human well-being right now. A 3 degrees C warmer world would seriously complicate every single aspect of sustainable living, from securing enough food and clean water to maintaining economic stability and public health.
We're talking more heat waves, bigger storms, that kind of thing.
Exactly. More frequent and intense extreme weather events, widespread disruptions to ecosystems we rely on, and huge challenges to basic human needs that could affect billions of people. This is why the scientific community increasingly recognizes the urgent need for additional strategies. Simply reducing emissions, while vital, might not be enough or fast enough to avoid the worst impacts.
So it's about needing more tools in the toolbox.
Precisely. Stabilizing the climate system at any temperature level requires a delicate balance between what we emit and what we manage to remove. In fact, most scientific scenarios that are consistent with limiting warming to 1.5 degrees C or even well below 2 degrees C already rely heavily on carbon removal technologies. They basically assume we'll need to actively pull billions of tons of accumulated CO2 out of the atmosphere annually in the second half of this century.
Billions of tons annually.
Yes, even with rapid emission cuts. That's a huge undertaking. And on top of that, solar geoengineering is also being discussed more frequently as a potential measure to directly alter Earth's energy balance and cool the planet, theoretically, much more quickly than emissions reductions alone could achieve.
Okay, so let's make that distinction really crystal clear. Nail down what each of these core concepts really means. What exactly is carbon removal?
Okay, carbon removal, CDR, It's all about actively drawing greenhouse gases, primarily carbon dioxide, directly out of the atmosphere. So think of it as addressing the cause of climate change, that buildup of CO2 trapping heat.
So vacuuming the sky, basically.
Sort of. Yeah, it's about cleaning up the excess carbon we've already emitted. The goal is to reduce the overall concentration of CO2 in the atmosphere.
Got it. And then solar geoengineering, SG, that sounds fundamentally different.
It is fundamentally different. Solar geoengineering aims to directly alter the planet's energy balance to reduce temperatures. So it's addressing a symptom of climate change, the warming itself, not the root cause, the CO2.
How does it do that?
Well, the main idea is to reflect more sunlight away from Earth, effectively putting a kind of planetary sunshade up, or making it easier for heat to escape. While both approaches aim to limit climate change impacts, it's crucial to understand they could also introduce entirely new risks and potentially substantial negative consequences for development outcomes, whether that's nationally, regionally, or internationally.
So potential unintended consequences.
Big time. Research in these areas is still relatively early, and the uncertainties are quite large. We just don't have all the answers yet about their full feasibility or safety. And this is precisely why more research and really careful governance is so incredibly important.
Now, let's transition to a specific, tangible example of carbon removal. Enhanced weathering. This is where it gets, I think, really intriguing because it builds on one of Earth's own natural processes.
Exactly. We're talking about accelerating the planet's very own way of drawing down carbon over geological time.
How does that work naturally?
Well, enhanced weathering, or EW, is based on the natural process of silicate rock weathering. Imagine rocks like basalt or olivine slowly breaking down over thousands or millions of years due to rain and atmospheric CO2. As they weather, they react chemically with CO2 and water, eventually locking that carbon away in dissolved forms, mostly bicarbonate, which ends up stored safely in the oceans. EW aims to drastically speed this natural process up.
How do you speed it up?
The main mechanism involves amending cropland soils with finely crushed silicate rocks, typically basalt. Basalt is a really abundant natural volcanic rock. It weathers relatively quickly compared to some other rocks, and it contains useful nutrients for plants. That makes it a compelling and accessible candidate for this.
So you crush up rocks and spread them on fields. How does that pull carbon out of the air?
Pretty much, yeah. When this finely crushed rock is applied to agricultural soils and mixed in, its minerals dissolve much faster than they would in a big chunk of rock, just because there's much more surface area exposed. This dissolution releases essential elements, these base cations like calcium, magnesium, sodium. And as this chemical reaction happens, CO2 from the atmosphere gets pulled into the soil water and is converted into that stable, dissolved bicarbonate ion form.
Okay, so the rock dissolves, reacts with CO2.
And turns it into bicarbonate.
Oh.
Then these bicarbonate ions travel through groundwater and rivers eventually to the ocean, where the carbon is stored for incredibly long periods. We're talking timescales greater than 10,000 years. So it's a very permanent storage.
Wow. And what's the potential scale of this?
The global potential is quite significant. Biogeochemical models suggest that if enhanced weathering with basalt were deployed across major agricultural regions worldwide, it could potentially sequester up to maybe 2 billion metric tons of CO2 annually.
2 billion tons.
Annually. Yeah, and that's even after accounting for the operational emissions, the energy needed for mining the rock, grinding it really fine, transporting it, and spreading it.
That's an immense scale. And what's particularly exciting, as you mentioned, is that a lot of this isn't just theory. There's been a significant large-scale field trial recently right in the heart of the U.S. Corn Belt.
That's right. At the University of Illinois Energy Farm, just south of Urbana, it ran for 4 years, 2016 to 2020.
And what crops were they growing?
They used maize corn and soybean crops, rotated annually, which is very typical for that region, the Midwest Corn Belt.
And what kind of rock did they use?
They used a specific type called Blue Ridge basalt rock dust. Interestingly, it was a byproduct from existing mining operations in Pennsylvania, which potentially helps with the economics and sustainability side.
How much did they apply?
They applied it annually at a rate of 50 tons per hectare. That sounds like a lot, but it works out to about 5 kilograms per square meter. Then they tilled it into the top layer of the soil. They also defined the particle size quite carefully, aiming for fine dust to maximize the surface area for weathering.
Okay, and how did they actually measure the carbon removal? Measuring CO2 uptake in a complex farm field sounds tricky.
It is very tricky. Conventional methods often struggle in these kinds of managed ecosystems because there are so many other biological and chemical processes happening. So they used a really sophisticated measurement approach. It involved quantifying the mass loss of those major base cations, calcium, magnesium, sodium from the applied base salt relative to the soil before treatment. They use something called isotope dilution mass spectrometry.
Whoa, okay, sounds complex.
It is. They essentially spiked soil samples with known amounts of specific isotopes of these elements, like calcium-42 or magnesium-26, and then measured how much those isotopes were diluted by the natural elements dissolving from the basalt. This allowed them to precisely track the rock dissolution and, by extension, the associated CO2 uptake. It was a necessary advance to get reliable data in these Midwestern croplands.
That level of precision is impressive. So what were the key results? What were the reproducible benefits they found? Did it actually remove carbon successfully?
Yes, the trial demonstrated clear success in carbon removal. They measured a cumulative CDR carbon dioxide removal of approximately 4 tons of CO2 per hectare per year for every 50 tons of rock they applied per hectare.
4 tons per hectare per year. How does that compare to the potential?
Well, it's significant, but it's worth noting that the theoretical maximum potential for CDR from this specific basalt, based on its chemistry, is much higher, around 17.9 tons of CO2 per hectare.
So there's room for improvement.
Absolutely. It suggests there's considerable room for optimization, maybe through even finer grinding of the rock, or perhaps using different types of basalt with mineralogies that weather even faster under those specific soil conditions, or maybe different application methods.
How does that compare to other ways farmers might store carbon, like planting cover crops or using no-till farming?
That's a good question. When compared to other agricultural practices aimed at building soil organic carbon, enhanced weathering, at least in this trial, showed notably higher annual rates of carbon sequestration.
Okay.
However, it's also important to acknowledge, full transparency, that more work is still needed to fully assess the fate of this captured carbon. We need to track it during river transport and confirm its final secure sequestration in coastal oceans before we can definitively say it's fully locked away long term. But the initial results are very promising.
And it wasn't just about CO2, was it? Did they find any other surprising climate benefits from applying this to salt?
They absolutely did, and this is a really significant co-benefit. They also observed substantial reductions in nitrous oxide emissions, N2O.
Nitrous oxide, that's laughing gas, right. But it's also a potent greenhouse gas.
Exactly. It's incredibly potent. Nitrous oxide has a 20-year global warming potential that's 273 times higher than CO2. So molecule for molecule, it traps way more heat.
Wow. 273 times.
Yeah, and the trial observed significant reductions in the cumulative N2O fluxes coming out of the soil, ranging between 14% and 41% reduction in 3 out of the 4 years of treatment.
That seems like a big deal, especially for agriculture.
It's huge. This is particularly important because maize and soybean production, especially in the U.S. Corn Belt with its heavy fertilizer use, accounts for up to a third of all North American N2O emissions. It's a major source.
So the powerful takeaway here is that enhanced weathering isn't just about CO2. It's also a surprising and potentially cost-competitive tool for tackling another major greenhouse gas. It gives farmers a dual climate benefit.
Exactly. When you quantify that N2O mitigation in CO2 equivalents, it improved the overall greenhouse gas removal by an additional 0.1 to 0.4 tons of CO2 equivalents per hectare per year. This positions enhanced weathering as potentially a cost-competitive N2O mitigation strategy compared to other tech-led practices farmers might use, like enhanced efficiency fertilizers or maybe drip irrigation or applying biochar. Some of those have additional costs, like specialized fertilizers costing around 28 taels extra per hectare for nitrification inhibitors. EW seems to provide this benefit almost as a side effect.
A dual benefit for climate and potentially for the farmer's wallet, too.
That's the hope. It truly offers potential for a dual benefit for the climate and for agricultural economics.
Okay, so we've got the climate benefits, CO2 removal, and N2O reduction. But what does this all mean for the farmers themselves? Beyond just carbon credits, were there direct benefits right there in the soil, which is, central to their whole operation?
That's a great question. And yes, the trial revealed several significant agronomic and soil fertility improvements. These are benefits that farmers would see directly. Firstly, enhanced weathering significantly increased the soil pH, making it less acidic at both the surface layer, 0-10 centimeters, and deeper down, 10-30 centimeters.
Why is that important?
Well, it counters soil acidification, which is a common problem in many agricultural lands due to things like fertilizer use and natural processes. Acidic soils can reduce crop yields and nutrient availability, and farmers often have to spend money applying lime to correct it. So EW offers a kind of natural liming effect as the rock weathers.
Okay, so healthier soil pH. What else?
Beyond pH, the trial unveiled a whole suite of direct benefits for the plants themselves, basically optimizing their access to vital nutrients. For instance, they saw significant increases in the total amount of nitrogen found in the grain biomass for both maize and soybean.
More nitrogen in the harvested crop? How did that happen?
In maize, it seemed to largely come from greater remobilization of nitrogen from the plant's leaves and stalk into the grain during the filling stage. This means increased nitrogen use efficiency. The plant was using the nitrogen it had more effectively. In soybean, which is a legume that can fix its own nitrogen, the increased grain nitrogen resulted from both increased uptake from the soil and enhanced N2 fixation. So multiple pathways were improved.
Fascinating. Any other nutrients affected?
Yes, quite a few. They also observed improved availability of molybdenum. Now, molybdenum might sound obscure, but it's a key micronutrient that helps plants, especially legumes like soybean, utilize nitrogen more effectively. The EW-driven pH increase seemed to mobilize molybdenum in the soil, leading to more of it in the plants and boosting nitrogen assimilation.
Okay, so N and Mo. What about the big ones? P and K, phosphorus and potassium.
Big improvements there, too. The total mass of phosphorus P and potassium K in the harvested grain increased significantly with the basalt treatment. The study estimated the annual basalt application at 50 TLKA1 released at least 7 kilograms of P per hectare per year and 23 kilograms of K per hectare per year.
That sounds like a decent amount of fertilizer value.
It is, and this offers a substantial potential economic benefit. EW practices could potentially substitute for a portion of expensive chemical fertilizers. Farmers have to buy things like urea phosphate, DAP, potash, which can cost hundreds, even close to $1,000 per ton these days. So this offers both potential economic savings for farmers and environmental benefits from reduced fertilizer production and runoff.
What about silicon? You mentioned silicate rocks.
Good point. Silicon is actually beneficial for crop productivity and resilience to stress. Now, typically, biologically available silicon in soil tends to decrease as pH rises, which is what happens with liming. But with enhanced weathering, the silicon released from the basalt weathering actually compensated for this pH effect. It maintained peak silicon levels in the plant biomass and could help redress the depletion of available silicon pools that can happen with intensive farming. This is another distinct advantage EW has over conventional liming, which only raises pH but doesn't add silicon.
That's incredibly detailed insight into how the soil and the plants are interacting. And you mentioned root responses earlier. Can you tell us more about those mechanistic insights? It sounded like the plants themselves were actively responding.
They absolutely were. This is where it gets really cool, I think. To gain a deeper understanding of how these nutrient changes were happening at a biological level, the researchers looked at the plant's gene activity specifically, gene transcription in their roots during the critical grain filling period.
What did they find?
What they found was remarkable evidence that the plants were actively optimizing their nutrient uptake systems at a fundamental genetic level in response to the EW treatment. For example, soybean roots showed an upregulation, meaning increased activity of genes responsible for transporting essential nutrients like ammonium, nitrate, phosphate, and potassium from the soil into the root cells. This makes perfect sense, aligning with the plant's need to absorb more of these newly available nutrients to fill the grain.
So the plant is turning up its nutrient pumps, basically.
Exactly. And interestingly, they also saw upregulation of genes related to symbiotic mycorrhizal fungi, which help plants acquire phosphorus and nitrogen. So the whole soil microplant system seemed to be responding. Maize roots, similarly, showed the strongest upregulation in phosphate transporter genes, consistent with their need for soil phosphorus. Interestingly, they saw some downregulation of potassium and nitrogen transporter genes in maize, which the researchers interpreted as consistent with the plant relying more on remobilizing those nutrients from its leaves and stems rather than taking up more from the soil late in the season.
Different strategies for different crops.
Yes, and genes for enzymes that help plants access phosphorus locked up in organic matter. Acid phosphatases and phytases were upregulated in both crops. They were basically unlocking more P. And remember the molybdenum link to nitrogen use. In soybean, genes related to building the molybdenum cofactor needed for nitrogen assimilation and the genes for the nitrate assimilation enzymes themselves, like nitrate reductase, were upregulated. This provides independent genomic evidence supporting the observed improvements in nitrogen nutrition.
Wow.
So, If we connect this to the bigger picture, these genomic insights independently support the observed changes in plant nutrient levels. They demonstrate a sophisticated biological response, showing the plants adapting to and efficiently utilizing the newly available nutrients from the weathered salt. It's almost like the plants are learning or optimizing how to thrive in this enhanced soil environment.
That's truly fascinating. The plants are actively tuning their internal systems. Okay, but what about the bottom line for farmers, the crop yields? Did all these soil and nutrient improvements actually lead to more grain? And crucially, were there any safety concerns? Like, did toxic heavy metals build up in the crops?
Good questions. Yes, yield enhancements were achieved, and importantly, these came along with significantly increased concentrations of key micro and macronutrients in the grain itself. Potassium, magnesium, manganese, phosphorus, and zinc were all higher. So it improved or maintained the crop's overall nutritional quality, which is a direct benefit.
And the safety aspect, trace metals.
This is really critical. Addressing a major potential concern for using natural rock products, the trial found no significant increase in potentially harmful trace metals like cadmium, lead, arsenic in the harvested grains of either maize or soybean. They also checked the soil pore water and the soil exchangeable pools, the readily available fraction, and found no significant accumulation after 4 consecutive annual treatments.
That's a relief.
It is. Molybdenum and copper, which are actually essential micronutrients, did increase slightly in the grain, consistent with their increased availability, but both remained well within safe dietary levels. This comprehensive data really helps alleviate concerns over the possible accumulation of bioavailable heavy metals in soils treated with enhanced weathering using this type of basalt. That's a major positive finding for the feasibility of widespread adoption.
Okay, that rounds out a really compelling case for enhanced weathering. From this study demonstrating not just carbon removal and N2O mitigation, but also direct, tangible benefits for soil health, nutrient cycling, crop nutrition, and potentially yield, all while appearing safe regarding trace metals. It really highlights the multifaceted potential. It seems like it could offer a genuine win-win scenario.
Based on this trial, yes, it looks very promising as a multi-benefit solution in these agricultural systems.
So, while enhanced weathering works by pulling carbon out of the atmosphere, addressing the cause, solar geoengineering takes a fundamentally different path. It aims to cool the planet by reflecting sunlight away, tackling the symptom. This brings us to the other major category of climate intervention, and one that, let's say, sparks considerably more debate and concern.
That's putting it mildly, yeah. Solar geoengineering, or SG, refers to a set of technologies and techniques that are still, it's important to stress, largely theoretical, but they all aim to directly alter the planet's energy balance.
How? What's the basic principle?
The principle is pretty straightforward. Either increase the reflection of incoming solar radiation before it gets absorbed by the Earth system, or somehow enhance the transmission of heat, the outgoing terrestrial radiation, back out into space. Make it easier for heat to leave. But it's absolutely vital to emphasize, again, that SG does not directly reduce anthropogenic greenhouse gas emissions. It does nothing about the CO2 already in the air or the CO2 we continue to emit. And therefore, it is not a substitute for drastic cuts in emissions or for adapting to the climate change already locked in.
Right. So if it doesn't fix the root cause, the CO2, why is it even being considered? That's the big question, isn't it?
It is. And the main reason it's on the table is because, in theory at least, it offers the potential for very rapid effects on global temperatures, potentially cooling the planet significantly within years, not decades or centuries.
Okay, so speed is the main selling point.
Speed and potential scale of cooling, yes. It could, theoretically, provide a way to quickly alleviate some of the most immediate and dangerous warming impacts, perhaps buying more time while the world transitions fully to a low-carbon economy. Think of it like a planetary emergency brake, maybe.
An emergency brake, but maybe one with some serious potential side effects. What are the main types of solar geoengineering being discussed, and what are their specific challenges?
Okay, the most prominent proposal, the one that gets the most attention, is stratospheric aerosol injection, or SAI.
Injecting stuff into the stratosphere, what kind of stuff?
The mechanism involves injecting tiny reflective aerosol particles, or more likely, precursor gases like sulfur dioxide, SO2, that then form aerosols into the lower stratosphere, typically around 20 kilometers or 12 miles altitude. The goal is to create a persistent haze layer up there that increases Earth's reflectivity, its albedo, scattering more sunlight back to space before it warms the surface. We actually have a natural analog for this, Large volcanic eruptions like Mount Pinatubo in 1991 naturally inject huge amounts of SO2 into the stratosphere and cause measurable global cooling for a year or two.
Okay, so mimicking volcanoes. What about the cost?
The estimated direct deployment costs for SAI are often cited as being potentially quite low, maybe in the range of US $10 billion per year globally, to achieve a significant cooling effect.
That sounds surprisingly cheap for tinkering with the whole planet.
It does sound low, and that's a key part of the debate. But those are just the costs of, say, the planes and the sulfur. The overall cost would be significantly higher. You have to factor in the immense requirements for global policy coordination, continuous, extensive monitoring systems to track effectiveness and side effects worldwide, security for the deployment infrastructure, building in redundancies in case something fails. It adds up quickly.
And the side effects. What are the known risks of spraying sulfur up there?
If standard sulfate aerosols were used, like from SO2, there's definite potential for some undesirable side effects. It could contribute to some acid rain, although maybe less than current pollution sources. It could lead to elevated sulfur levels in the lower atmosphere. And a big concern is that it could delay the recovery of the stratospheric ozone layer, which protects us from harmful UV radiation.
Delaying ozone recovery sounds bad.
It's definitely a concern. However, it's worth noting that research is also looking into other potential substances besides sulfur. Things like calcite aerosols, basically fine limestone dust. Some studies suggest these might actually have positive impacts on ozone, potentially accelerating its recovery, and might counteract acidification instead of causing it. But that's still very early research.
What about other impacts? Would it change the sky? Affect plants?
Potentially, yes. The aerosols would scatter sunlight, which could make the sky appear hazier or whiter, and perhaps make sunsets less vibrant. That has potential cultural implications. More practically, this dispersal of light reaching Earth's surface, more diffuse light, less direct sunlight, could affect plant growth. Some crops might benefit, others might suffer. This could have knock-on effects for agriculture and food security that are still poorly understood.
Okay, that's SAI. What about modifying clouds? That sounds a bit less direct, maybe.
It's another major category, yes. Cloud modifications. This can be done over land or, more commonly discussed, over water surfaces. The basic idea is seeding clouds with tiny particles to influence their properties, mainly their reflectivity.
How do you seed a cloud?
Over oceans, the main proposal is called marine cloud brightening. This involves spraying fine seawater particles, basically tiny salt crystals, into the air from ships moving beneath low-lying marine stratocumulus clouds. These extra particles act as cloud condensation nuclei, supposedly leading to more smaller cloud droplets. This, in theory, makes the clouds brighter and more reflective.
Brighter clouds reflect more sun.
That's the idea. Another concept involves seeding high-altitude ice clouds, called cirrus clouds. These clouds tend to trap heat. Seeding them might thin them out or make them dissipate faster, allowing more heat to escape from Earth into space.
What are the downsides there?
Well, the physical effects are highly dependent on the specific particle types used, the quantities, the exact location, timing, and even the emissions from the ships or planes doing the seeding. Seawater spraying might seem relatively benign, perhaps similar to natural sea salt fluctuations, but very localized deposition could potentially cause corrosive effects on coastal infrastructure, or negative impacts on coastal soils if it drifts inland. But the biggest challenge here is that the physics of clouds is incredibly complex and still not fully understood by climate science. There's a very real risk of significant adverse implications for regional weather patterns, ecosystems, and agriculture due to unintended changes in rainfall or temperature that we just can't predict accurately right now. Uncertainty is huge with cloud modification.
Okay. And the last category you mentioned, making surfaces brighter.
Right, surface albedo modifications. This is maybe the most intuitive one. It simply involves making various surfaces on Earth brighter so they reflect more incoming solar radiation.
Like painting roofs white.
Exactly. That's a common example for urban areas, white or reflective roofs and pavements. But people have also proposed doing it on larger scales. Maybe covering deserts with reflective materials, genetically engineering crops to be lighter in color, spreading foam or reflective beads on parts of the ocean, or polar ice caps.
Covering deserts? That sounds ambitious. What are the issues?
The physical implications of doing this on a really large scale could be substantial. Covering vast areas with artificial materials would obviously affect local ecosystems and could potentially alter local or even regional hydrological cycles, affect plant growth patterns, and disrupt the natural transport of dust and minerals. Plus, the production of these materials, whether it's specialized paint, reflective foils, or plastic beads, could cause significant environmental harm and generate greenhouse gas emissions during manufacturing and transport. And then, as these materials inevitably break down or erode, they could lead to plastic or chemical pollution in soils, rivers, and oceans.
And would it even work globally?
The effectiveness of surface albedo modifications for significant global cooling is pretty unclear, mainly because any application would likely be quite patchy and localized. They are, however, seen as having more promise as a localized adaptation strategy. Reducing urban heat islands with cool roofs, for example, is already happening and has clear local benefits. Or perhaps localized efforts to brighten areas around vulnerable glaciers might help slow their melting, but probably not a global climate fix.
So it sounds like across all these solar geoengineering approaches, there are significant uncertainties and potential challenges just looming large.
Absolutely. That's the bottom line right now. The overarching challenges are numerous and serious. Huge uncertainties persist regarding their basic feasibility, their effectiveness across different regions, and the full range of risks involved. A major concern, particularly with SAI, is the potential for rapid termination shock. If you were implementing SAI for decades and then it suddenly stopped, maybe due to political conflict, economic collapse, or technical failure, global temperatures could shoot up extremely rapidly, potentially much faster than ecosystems or human societies could adapt. That could be catastrophic.
A rebound effect.
A very dangerous rebound effect. Then there's the expectation of uneven regional results. Some areas might benefit from the cooling, but others could experience detrimental changes in temperature or, crucially, precipitation patterns, leading to droughts or floods. Who decides which outcome is acceptable? And critically, as we said, SG does nothing to address ocean acidification, the other CO2 problem, which is driven directly by high CO2 concentrations dissolving in seawater and threatens marine ecosystems worldwide.
And the governance.
Oh, the governance challenges are perhaps the biggest hurdle of all. How do you get global agreement on deploying something like this? How do you manage it collectively? What prevents a single country, or even a wealthy individual, from trying to deploy it unilaterally, potentially against the wishes of others? The potential for international tensions and conflict is immense. So if we connect this to the bigger picture, solar geoengineering presents this incredibly complex risk trade-off. It could potentially reduce some significant climate impacts, like extreme heat, but it also introduces a whole host of novel, potentially large-scale risks and major governance questions that we are currently nowhere near resolving.
Okay, so we've looked at the science, the potential, the risks of these two broad categories, carbon removal and solar geoengineering. But now let's broaden the lens. Beyond the direct environmental impacts or temperature changes, what does the deployment of these technologies actually mean for human well-being, for society, for the kind of world we want to build?
Yeah, this is absolutely critical.
And this is where the Sustainable Development Goals, the SDGs, become a really useful framework, don't they? They give us a way to assess the wider implications across many different dimensions of human life: poverty, hunger, health, equality, peace, things that are often overlooked when climate discussions focus only on temperature targets or tons of CO2.
Exactly. The SDG framework provides that holistic view. And the overarching findings from reports that have tried to map the potential impacts of climate interventions onto the SDGs are, well, they're quite stark and, frankly, quite sobering.
How so?
First, it's clear that current climate change is already hindering the delivery of the SDGs significantly across the board. That's the baseline. But even more critically, the analysis suggests that the large-scale deployment of either carbon removal or solar geoengineering is expected to affect at least 3/4 of all the SDGs.
3/4? That's huge. 13 out of 17 goals.
Minimum. And here's the really critical part. Some forms of these interventions, depending on how they're implemented and at what scale, could potentially negatively affect the delivery of more than half of all SDGs, so impacting at least 9 out of the 17 goals in a detrimental way.
Which goals are most at risk?
The key risks identified consistently pop up across a wide range. SDG 1, no poverty; SDG 2, zero hunger; SDG 3, good health and well-being; SDG 6, clean water and sanitation; SDG 7, affordable and clean energy; SDG 8, decent work and economic growth; SDG 14, life below water; SDG 15, life on land; and SDG 16, peace, justice, and strong institutions. Basically, all the core elements of sustainable development.
Wow. How do these impacts manifest? What are the common threads?
They generally fall into two broad categories. First, you have the direct physical side effects. These relate to things like land use competition affecting food security, impacts on water quality and availability, direct health effects from materials used, changes in energy systems, impacts on economic productivity, like fisheries or farming, and effects on biodiversity both on land and in the oceans. Second, you have the broader socioeconomic or political implications. These include things like economic costs and benefits, potential cultural impacts, the opportunity costs. What else could we have done with that money and effort? The potential for increased political tensions between countries, and the sheer governance demands these technologies would impose. What's really fascinating here, and maybe a bit daunting, is how interconnected all these issues are. An intervention designed purely to address one climate problem, like temperature, can have these cascading effects across multiple dimensions of human development, sometimes in ways we might not initially expect.
Okay, let's dive into some specific examples for these key SDGs just to make it more concrete. Starting with SDG 1, no poverty. How could these interventions affect efforts to end poverty globally?
For SDG 1, there's a significant concern that the potentially massive public spending required for widespread carbon removal or solar geoengineering could divert funds away from existing poverty alleviation programs like education, healthcare, or social safety nets. The opportunity cost argument.
Resources are finite.
Exactly. Additionally, if regulations are imposed on, say, smallholder farmers, perhaps requiring them to adopt certain land management practices for carbon removal or restricting crop types, it could inadvertently harm their income generation, potentially pushing them further into poverty if not designed very carefully.
Is there an upside for poverty?
Well, conversely, if these technologies are successfully deployed and do significantly reduce climate impacts like droughts or floods that disproportionately harm the poor, they could potentially reduce overall public spending needs on disaster relief and recovery in the long run. This could indirectly benefit poverty reduction efforts. It's a complex balance sheet.
Okay. And for SDG 2, zero hunger. How might these interventions affect global food security? This seems like a really big one.
It's a huge concern, especially with land-based carbon removal. Land use conflicts are a major worry. If we need vast areas of land for large-scale afforestation, planting new forests, or for growing bioenergy crops, often part of a strategy called BCS bioenergy with carbon capture and storage, that land might displace land currently used for food production.
Competing for land.
Yes, and this could particularly impact subsistence farming communities in vulnerable regions, potentially driving up food prices or reducing local food availability.
What about SG impacts on food?
With stratospheric aerosol injection, the potential changes in light scattering more diffuse light, less direct light, could impact plant growth and photosynthesis differently for various crops, possibly reducing overall agricultural yields in some key breadbasket regions. That's still uncertain, but a definite risk. Ocean fertilization, another proposed CDR method, aims to stimulate phytoplankton growth to absorb CO2, but it could also disrupt marine food chains in unpredictable ways, potentially harming fisheries that millions rely on. And there's also the small but real risk of CO2 leaks from geological storage sites, harming nearby plants or livestock.
Can these food security risks be managed?
Potentially, yes. Careful policy design is crucial. For instance, policies could be designed to financially benefit vulnerable farmers for participating in certain carbon removal strategies on their land, rather than simply displacing them. But avoiding negative impacts on SDG 2 requires very careful planning and consideration of local contexts.
What about SDG 3, good health and well-being? How might these technologies impact our health directly or indirectly?
On the negative side, there's a risk of respiratory problems from exposure to airborne substances used in some of these processes. Think about dust from mining and grinding minerals for enhanced weathering, smoke or particulates from biochar production if not well controlled, or even direct inhalation exposure to the particles injected for stratospheric aerosol injection, especially for deployment workers or populations near deployment zones. SAI using sulfates could also influence the ozone layer and UV radiation levels reaching the surface, which might affect skin cancer rates. Changes in atmospheric chemistry could also potentially affect the safety or quality of surface water sources used for drinking.
But there could be health benefits too, right, from reducing climate change itself?
Absolutely. That's the other side of the coin. Successfully reducing climate change impacts fewer deadly heat waves, less malnutrition from crop failures, reduced spread of vector-borne diseases, fewer injuries from extreme weather events could yield very significant public health benefits globally. And some localized interventions like surface albedo modification, cool roofs in cities, could directly reduce urban heat islands, improving health and well-being for millions during heat waves.
Moving to SDG 6, clean water and sanitation. Water seems intrinsically linked to many of these ideas.
It really is. Land-based carbon removal techniques that rely on growing biomass, like large tree plantations or bioenergy crops, can have significant impacts on water availability. These thirsty plants can consume substantial amounts of water, potentially exacerbating water scarcity in already dry regions. That's a major constraint. Geological CO2 storage also carries risks. While generally considered safe if sites are well chosen and monitored, there's a potential, however small, for leaks to affect groundwater chemistry, possibly contaminating sources used for drinking water if not managed extremely carefully.
And SG impacts on water.
SAI, especially using sulfates, could contribute to the acidification of lakes and streams through altered atmospheric deposition, although, as mentioned, some proposed alternative aerosols like calcite might actually counteract acidification. Mineral-based processes like enhanced weathering or ocean alkalinization inevitably involve moving large amounts of minerals around, which could introduce unwanted material flows or chemical changes into rivers, lakes, and coastal waters if not managed properly.
Any positive water impacts?
Yes, some land use changes associated with CDR could be beneficial for water. For instance, restoring degraded ecosystems or strategic afforestation in certain areas can actually improve soil water retention, regulate river flows, and help prevent flash floods. So it depends heavily on the specific approach and location.
How about SDG 7, affordable and clean energy? Where's the link there?
Energy is a huge factor, especially for carbon removal. Most CDR options have significant energy requirements. Think about the energy needed for mining and grinding billions of tons of minerals for enhanced weathering, or the very high energy demands of direct air capture, DAC plants that suck CO2 directly from the air, or the energy needed to compress CO2 and transport it for storage.
So CDR needs energy. Does it compete with other energy needs?
It definitely could. This energy demand could compete with other societal energy uses, potentially raising energy prices, or worse, relying heavily on fossil fuels if clean energy sources aren't scaled up massively alongside CDR deployment, which would defeat the purpose.
What about SG and energy?
SAI could have interesting interactions with solar power. By scattering sunlight, it might slightly reduce the efficiency of concentrated solar power plants, which use mirrors to focus direct sunlight, but it could potentially increase the efficiency of standard solar photovoltaic PV panels, which can utilize diffuse light more effectively. It's complex, and locally, as we mentioned, surface albedo modifications in cities could reduce the energy demand for air conditioning during hot weather, which is a positive energy link.
And SDG 8, decent work and economic growth. How does this all play out economically?
There's potential for negative economic impacts. Competition over key resources like land, fresh water, and certain minerals needed for these interventions could drive up commodity prices, negatively impacting existing economic activities that rely on those resources, like fisheries, agriculture, or even construction. The high costs of many carbon removal technologies, especially DC, which is currently among the highest, might require significant public spending or subsidies. This creates opportunity costs that money could have been invested in other growth-supporting activities like education or infrastructure. And right now, most CDR and SG technologies lack economically viable business cases on their own without substantial incentives or high carbon prices.
But could they also create jobs?
Yes, that's the potential upside for SDG 8. Developing and deploying these novel technologies could stimulate significant industrial innovation, create new jobs in research, development, manufacturing, deployment, and monitoring. It could potentially foster new green industries, though the net effect on overall employment and growth is still debated.
Next, SDG 10, reduced inequalities. This feels like a really critical, thorny issue. How might these interventions affect inequality?
It's incredibly important and complex. There's a very real risk that harmful side effects from these interventions could disproportionately affect already disadvantaged populations or regions, thereby increasing inequality both within and between countries. For example, if SG altered rainfall patterns, it might benefit agriculture in one region while causing drought and hardship in another, likely poorer region.
And the research itself might be biased.
That's another major concern. Currently, most of the research and funding for CDR and SG is heavily concentrated in the global north. This risks creating significant biases, potentially overlooking issues, risks, or even potential benefits that are particularly pertinent to developing countries. Their unique needs, vulnerabilities, and environmental contexts might not be adequately considered in research design or technology development.
Is there any way they could reduce inequality?
Well, the main argument here is that by reducing the overall impacts of climate change, these technologies could theoretically improve development outcomes for the most disadvantaged communities globally, who are often on the front lines and suffer the most from climate impacts like sea level rise or crop failures. So, if deployed perfectly equitably with no negative side effects, maybe. but that's a huge if. It remains a major area of concern.
For SDG 13, climate action itself, it seems obvious these are related, but what are the specific nuances or potential conflicts?
Well, carbon removal is now widely considered by climate science bodies like the IPCC to be a necessity, not an option, to meet the agreed-upon 1.5 degrees C or 2 degrees C global warming targets. So in that sense, CDR is climate action. It directly contributes by reducing net atmospheric CO2. Solar geoengineering is different. While it could, in theory, mask some climate impacts and potentially buy time for emissions cuts, there are very significant concerns about moral hazard.
Moral hazard, meaning
Meaning that the mere existence or potential deployment of SG as a perceived quick fix for temperature could reduce the political will and public pressure needed for the difficult but essential task of drastically cutting greenhouse gas emissions at their source. This raises that really important question. Are these solutions potentially a dangerous distraction, a shortcut to avoid harder choices about transforming our energy systems and consumption patterns, or are they a vital tool in a truly comprehensive climate strategy?
a tough question. What's the consensus?
The strong consensus among most scientists and policy experts who study this is that these interventions, if ever deployed, absolutely must complement, not replace, drastic and rapid emissions reductions. They cannot be seen as an alternative.
Okay. And finally, SDG 15, life on land. How might terrestrial ecosystems and biodiversity be impacted?
Again, land-based carbon removal carries significant risks here. The sheer scale of land use changes potentially required for options like large-scale biomass plantations for BECS or massive afforestation programs could severely impact natural terrestrial ecosystems and biodiversity. Replacing diverse natural habitats with vast monocultures of trees or energy crops is generally bad for wildlife and ecosystem health. Associated water use can also drastically alter habitats.
Can CDR be good for biodiversity?
It can be, if done right. If CDR focuses on restoring degraded lands, planting diverse native forests that are appropriate for the local ecology, or improving soil health on existing agricultural lands, then it can contribute positively to biodiversity protection and ecosystem restoration. It really depends on the approach. Solar geoengineering, like SAI, could also affect terrestrial ecosystems through changes in atmospheric chemistry, for example, ecosystems sensitive to acidification, or conversely, alkalinization from different aerosol types, or through changes in sunlight patterns affecting plant communities. The impacts are still not well understood. So to reiterate and wrap up this section, the potential impacts of these climate interventions on the SDGs are incredibly widespread, complex, and interconnected. They vary hugely depending on the specific technology, the scale of deployment, how policies are designed to guide them, and the specific governance context. And it's always crucial to remember the counterfactual. Not deploying these technologies and allowing climate change to proceed unabated also has devastating implications for nearly all the SDGs. So it's a challenging spectrum of risks, benefits, and trade-offs that requires extremely careful, holistic, and equitable navigation.
Okay, so we've talked about the science, the risks, the societal implications. Now let's get to the really pragmatic questions. How scalable and cost-effective are these interventions, really? And how might they fit into our overall economic strategy for tackling climate change? When might a tech rescue seem more viable than just focusing on systemic change like emissions cuts?
Right, the economics and scalability are absolutely key. When we look at carbon removal, the reality is that many of these technologies are largely untested at the massive scales needed to make a significant dent in atmospheric CO2. And generally, they are substantially more expensive, often an order of magnitude more expensive, than most current efforts to simply reduce emissions at the source.
Can you give some cost examples?
Sure. For enhanced weathering, the estimates we saw in the recent literature review and supported by the trial put the cost somewhere in the range of US $60 to $200 per ton of CO2 removed. That's considerable, though potentially competitive with some other CDR methods. Direct air capture and storage, DSE, which often gets a lot of attention, is currently one of the highest cost options. Estimates vary wildly depending on the technology and energy source, but they often range from maybe US $200 per ton of CO2 at the very optimistic low end, up to US $600 or even $1,000 per ton for current pilot projects. That highlights really significant economic barriers without strong government incentives or very high carbon prices.
So D-Day is expensive. What about the scale needed for EW?
Well, think about it. Large-scale mining, crushing literally billions of tons of rock into fine dust, transporting it potentially long distances, and spreading it accurately. These operations for enhanced weathering and similar mineral-based approaches like ocean alkalinization would require absolutely massive logistical efforts and substantial energy inputs, adding significantly to the overall cost and operational complexity. Scaling these up means moving an almost unbelievable amount of material around the globe.
Okay, so CDR, potentially effective, addresses the root cause, but generally expensive and logistically challenging to scale. What about solar geoengineering on the cost front?
Solar geoengineering, particularly stratospheric aerosol injection, is often presented quite differently in economic discussions. It's frequently highlighted as having potentially very low direct deployment costs. Remember that $10 billion per year globally estimate for SAI, and capable of producing very rapid, large effects on global temperature.
That sounds almost too good to be true. Low cost, fast results.
Well, that's the hook. But those figures, as we discussed, don't tell the whole story. They typically only cover the direct operational costs, like the planes and the sulfur. The overall societal cost would inevitably be much, much higher. You have to account for establishing and maintaining a global governance framework, continuous worldwide monitoring systems, ensuring security, building in redundancies, researching and potentially compensating for negative regional side effects. The list goes on. And fundamentally, it's still completely unclear whether any SG technology will ever be technically reliable enough, politically acceptable, economically sensible when all costs are included, or socially feasible and governable on a global scale. The uncertainties remain immense. So what's fascinating here, again, is that economic contrast. Carbon removal is generally expensive and relatively slow to take effect climatically, but it tackles the root cause by actually removing CO2. Solar geoengineering is theoretically cheaper and faster to cool the planet, but it only masks a symptom, warming, while doing nothing about the underlying CO2 problem and introducing a whole new suite of profound risks and dependencies.
Okay, let's unpack this further then. What happens when economists try to factor these possibilities, especially the cheap and fast SG option, into their big computer models that try to figure out the optimal climate policy pathway for the world? How does the mere option of solar geoengineering, even with all its risks, change the economic calculus?
This is where things get really interesting and also quite controversial. When standard integrated assessment models, or IAMs tools like the DICE model developed by Nobel laureate William Nordhaus, are adapted to include solar geoengineering as a potential policy choice alongside emissions cuts and carbon taxes, the findings are pretty consistent and quite striking.
What do they show?
The most robust finding is that including SG as an option unambiguously lowers the optimal carbon tax or carbon price that the model recommends. In some simulations, this optimal carbon price can end up being 30% to 45% lower in the long run, say after 100 or 200 years, compared to scenarios where SG isn't available.
Why does it lower the carbon price? That seems counterintuitive if we still need to cut emissions.
It's because SG, by directly manipulating the Earth's energy balance, radiative forcing, can reduce global temperatures much more quickly and, in these models, much more cheaply than relying solely on costly emissions abatement. This rapid temperature effect essentially decreases the urgency and therefore the calculated economic benefit of implementing very high carbon prices immediately to force rapid abatement. The model sees SG as a cheaper way to achieve the temperature goal, at least partially.
So if the carbon price is lower, does that mean we cut emissions less?
Yes, that's the direct consequence in these models. The optimal level of emissions abatement, how much we reduce our carbon output compared to business as usual, can be significantly lower, sometimes up to 25 percentage points lower when SG is available. And the point at which the model suggests we should reach net zero carbon emissions could be delayed by decades.
So the models basically say, use SG, keep temps lower, but let CO2 concentrations go higher for longer.
Precisely. The models show that if SG is allowed as a policy tool, atmospheric carbon concentrations can end up being considerably higher than in an abatement-only scenario. But global average temperatures can still be kept lower, perhaps meeting a target like 1.5 degrees C or 2 degrees C that would be much more expensive or even impossible to reach otherwise in the model. This perfectly illustrates SG's role in these economic frameworks as an imperfect substitute for emissions abatement. It substitutes for abatement in controlling temperature, but it doesn't substitute for abatement in controlling carbon concentrations.
Which means it doesn't address things like ocean acidification.
Exactly. It addresses the temperature-related climate damages in the model, but not the damages driven directly by high CO2 concentrations, like ocean acidification or direct physiological effects on plants. And that highlights a crucial trade-off. The more damages a specific economic model attributes directly to CO2 concentration itself, rather than just temperature, the less intensively solar geoengineering gets deployed in the model's optimal solution. Its value decreases if non-temperature CO2 damages are considered significant.
What does this mean for overall economic welfare, according to these models?
The model suggests that ignoring the possibility of SG, if it were indeed a viable and relatively low-damage option, could lead to suboptimal policies. Policies that abate too much too soon, cost too much economically, and rely on an artificially high carbon price. This miscalculation, according to the models, can result in significant economic welfare losses, for example. One study estimated that net global GDP could be over 1.5% lower in scenarios that ignore SG compared to those that deploy it optimally. That represents a substantial deadweight loss to the global economy in these calculations.
Are these results sensitive to uncertainty? Climate change is full of uncertainty.
Very much so. Another key finding is that the optimal level of SG deployment is actually more sensitive to uncertainties about the climate system. Things like the equilibrium climate sensitivity, how much the planet warms for a doubling of CO2, than the optimal level of emissions abatement is. This has led some economists to suggest that SG could potentially serve as a form of insurance against unexpectedly harsh or abrupt climate damages. Maybe it shouldn't be deployed continuously, but held in reserve and deployed only if global temperatures cross certain dangerous thresholds, say 2 degrees C or 2.5 degrees C increase, as a way to manage tail risk.
And how sensitive is it to the potential damages from SG itself?
Extremely sensitive. The optimal level of SG deployment in these models is highly dependent on the assumptions made about the cost or damages caused by SG itself, like those regional side effects or termination risks. If those damages are assumed to be low, the models tend to recommend deploying SG very intensively. If the assumed damages are high, then deployment is much lower or non-existent. This just underscores how critical it is to actually understand the real-world risks and side effects of SG before relying on these kinds of economic modeling results.
That's a profound economic implication, isn't it? The very idea that a potential tech rescue, even a risky one like SG, could significantly alter optimal economic policy, potentially freeing up resources by lowering abatement costs, but also fundamentally shifting the kinds of risks we face and the ethical trade-offs we need to consider. It shows how deeply intertwined these technological choices are with global economic strategy and the fundamental decisions we have to make about our collective future.
Absolutely. These models provide insights, but they also embed a whole set of assumptions and values that need careful scrutiny. They don't give us the right answer, but they do illuminate the potential economic pressures and trade-offs involved.
So, where do we go from here? We've covered a lot of ground: the science, the potential benefits, the significant risks, the societal impacts, the economic modeling. It's clear these aren't simple plug-and-play solutions, and there's still just a massive amount we don't know.
That's exactly right. The sheer complexity and the multitude of unknowns really underscore a critical, urgent need for two things: much more targeted research and the development of robust, adaptable governance frameworks.
Okay, let's break that down. What are the biggest research gaps that need filling?
They're extensive really across the board. First, just focusing on the effectiveness and physical impacts. For solar geoengineering, we urgently need to confirm if it can actually consistently reduce overall climate change impacts across different regions and different climate variables, like rainfall, not just temperature, without causing unacceptable adverse local or regional weather changes or other unforeseen environmental problems. That's a huge scientific challenge. Then there's the whole realm of socioeconomic impacts. We need much more research on how these interventions would play out differently in different regions of the world. How would they affect economies, for example, through changes in prices of key resources like land, water, or energy? What are the detailed impacts on agriculture and food security globally and locally? What are the potential direct and indirect health impacts, especially for vulnerable populations? These questions are vastly under-researched compared to the basic physical science.
What about environmental impacts beyond just climate?
Yes, the broader environmental impacts need much more study. For instance, the detailed ecological effects of dispersing large quantities of minerals for enhanced weathering or various types of aerosols for SG on ecosystems both terrestrial and aquatic are not well understood at scale. How do these materials interact with soil microbes, plankton, sensitive species? We need answers. From a policy perspective, we need research on how best to actually design policy instruments to mobilize CDR or potentially govern SG research and deployment. And crucially, what are the implications of different policy choices for achieving the Sustainable Development Goals? How do we ensure policies are equitable? And finally, underpinning all of this is the need for research on governance. How do we actually manage research responsibly? How can we potentially manage deployment in a way that supports sustainable development globally and actively works to reduce negative impacts and ensure equitable outcomes? This really raises that fundamental question. How can we ensure that science and technology, especially powerful planetary scale technologies like these, genuinely serve global well-being and equitable development, rather than inadvertently creating new problems or exacerbating the existing inequalities we already struggle with?
It sounds like the kind of research needed has to be fundamentally different, much more inclusive and collaborative than perhaps traditional lab-based science.
Precisely. There's an absolutely crucial need for transdisciplinary research, bringing together natural scientists, engineers, social scientists, economists, ethicists, legal scholars, and also for geographically diverse research.
What does geographically diverse mean in practice?
It means actively involving non-academic stakeholders like local communities, farmers, indigenous groups, civil society organizations whose perspectives and knowledge are vital but often excluded. And critically, it means significantly strengthening the funding for and participation of researchers from the Global South.
Why is participation from the Global South so important here?
It's vital to reduce the inherent blind spots and biases that come from research being dominated by institutions and perspectives from wealthy northern countries. We need to understand the unique regional sensitivities, vulnerabilities, priorities, and potential impacts in Africa, Asia, Latin America, and small island states. Their voices and expertise are essential for developing equitable and effective solutions, or for identifying unacceptable risks that might be overlooked otherwise. This also involves developing common assessment principles and metrics for evaluating the impacts on the SDGs that are globally applicable but locally relevant. And it includes actively working to increase the representation of women and other underrepresented groups in this research field to avoid inadvertently embedding or exacerbating existing societal inequalities through the science itself. Furthermore, alongside the natural and economic sciences, we need to significantly ramp up dedicated social science and humanities research.
Why is that so important?
Because we need critical reflection on the very role of science and technology, particularly these large-scale interventions, within the broader context of the Sustainable Development Goals and societal values. We need humanists and social scientists to help us understand the historical context, the cultural assumptions, the political dynamics, and the ethical paradigms that are shaping how these technologies are being developed and discussed. It's not just about figuring out what we can do technically, but deeply considering what we should do, why, who benefits, who bears the risks, and who gets to decide. These are fundamentally social and ethical questions.
Okay, so a massive research agenda needed. But beyond the research, you mentioned governance. The governance challenges seem truly daunting, maybe even more so than the technical ones, especially for something like solar geoengineering with global reach.
They are incredibly daunting. The critical governance challenges are numerous. First and foremost is figuring out how to design governing structures internationally and nationally that ensure these technologies, if pursued, genuinely complement and support, rather than distract from or undermine, the primary goal of strengthening and accelerating greenhouse gas emissions reductions. That moral hazard issue needs active governance to mitigate it.
How do we make decisions about this stuff?
That's the core challenge. We need to establish clear, transparent, accountable, and inclusive decision-making structures. This has to involve fostering broad, informed public dialogue globally about the risks, benefits, and ethical dimensions, so that choices about research directions, potential pauses, or any eventual deployment are made legitimately and reflect societal values, not just techno-economic calculations. We also need to figure out how to build governance capabilities in countries around the world that have vastly differing resources, scientific capacity, and institutional strength. How do we ensure meaningful participation and prevent a situation where only a few powerful actors dictate the terms?
What about international versus national roles?
Differentiating the appropriate responsibilities between national governments and international institutions is key. What needs global agreement versus what can be managed nationally? And we have to realistically address the political and commercial interests that could significantly challenge effective international governance. There will be actors who see strategic or economic advantages in pushing certain paths, potentially undermining cooperative approaches. What does this mean for you, the listener? It means that even as we push the boundaries of potentially powerful scientific solutions, the human element, how we organize ourselves, how we decide collectively, how we cooperate across borders, how we ensure fairness and equity for everyone, especially the most vulnerable, is just as crucial, if not ultimately more crucial, than the specific technology itself. And finally, there's the practical challenge of collective monitoring and verification. If any of these large-scale interventions were deployed, we'd need robust international systems to monitor their effects, both intended and unintended, verify performance, and share data openly. This poses huge technical and political challenges, requiring new levels of international scientific collaboration and data sharing. But perhaps, paradoxically, tackling this shared challenge, if done right, could itself strengthen international cooperation and build trust among nations as they work together to understand and manage these powerful planetary interventions.
Wow. What an incredible and slightly dizzying journey into the frontiers of climate intervention. We've explored the really tangible promise of enhanced weathering, not just for carbon removal, but also for those surprising co-benefits in agriculture.
The Corn Belt trial was really illuminating there.
And then we delved into the rapid cooling potential, but also the profound risks and ethical quandaries of solar geoengineering. Feels like opening Pandora's box a bit.
It certainly carries that weight, yes.
And crucially, we've tried to unpack the profound interconnected implications that deploying any of these technologies at scale could have for literally every aspect of global sustainable development hitting so many of those SDGs, for better or worse.
Yeah, the interconnectedness is really the key takeaway for me. Nothing happens in isolation. And if we connect this all back to the bigger picture, I think it becomes incredibly clear that the path to a truly sustainable future isn't just about picking the right technologies off a shelf. It's fundamentally about defining our collective values and deciding what kind of world we actually want to live in.
Defining our values.
Yes. Because the potential deployment of these powerful interventions forces us, globally, to confront really difficult questions. What future are we truly aiming for? Are we willing to make the complex, sometimes uncomfortable but equitable choices required to get there, like fundamentally transforming our energy systems and consumption patterns? Or are we perhaps tempted to seek what might seem like a simpler technological fix, even if it carries unknown or potentially unfair risks? We have to understand that while technology offers incredibly powerful tools, the societal, ethical, and political frameworks that guide how we develop and use those tools are equally, if not more, critical. It demands not just scientific literacy from all of us, but also deep ethical reflection, broad public engagement, and unprecedented global cooperation.
A powerful thought to end on. It's not just about the what and how, but the why and who. Thank you for joining us on this deep dive into climate's new frontiers. We really encourage you, our listeners, to continue your own exploration of these vital, complex topics and to consider how these cutting-edge interventions might shape our shared world. Until next time, stay curious.